I really appreciate this opportunity to share my research with you on sustainable systems. There's going to be no music, no videos, more traditional format here. Whoops. This doesn't look like my presentation. Should I be? Great, thank you very much, appreciate it. So I'm going to be talking about sustainable systems and focusing on three systems that are of importance to all of us: mobility, building, specifically residential homes, and food systems. And I'm going to connect two themes of our conference here, industrial metabolism and manufacturing, with cities, which we talked about yesterday. And to do that, I'm going to use the modeling approach in my research, which is life cycle assessment. So we're going to look at combining, which typically happens outside of the city, the production with the consumption and the use, which happens in the city. And for this framework, we model each of these activities. As engineers, we do a boundary around the system, and we look at flows of material and energy into the system, and we look at what goes out of the system, including our products. And this provides us an ability to evaluate sustainability performance. We see how energy is distributed across the life cycle, and we could see areas for focus. So we're going to start out with mobility. And we did the first comprehensive life cycle model of a mid-sized vehicle working with Chrysler, Ford, and GM and material industries. And we wanted to develop a benchmark for evaluating improvement of the vehicle. So after 3 years of modeling, this is what you get as a result. This is a life cycle profile of that vehicle in gigajoules, and it's showing you the distribution across stages. So you can see our material production, the manufacturing, and the life cycle energy is dominated by the use phase, which consumes 85% of the energy over the life cycle. You total it up, and you get 1,000 gigajoules of energy going into the system. Now, if you look at improving this system, one of the strategies that's being used by the industry is lightweighting. So if we substitute conventional steel with aluminum, this will go down. But you're going to get increases in the material production because aluminum is very energy intensive. It depends on where you manufacture the aluminum and what the electricity is used from the grid. That's going to really influence the result. So we're doing work on lightweighting. We're doing work on electrification. I want to show you some results for modeling a plug-in hybrid electric vehicle. And this is the Chevy Volt. So this is the total life cycle greenhouse gas emissions associated, and it's greenhouse gas emissions, grams of CO2 equivalents per mile on the y-axis. And on the x-axis, what you see is the utility factor, which is the amount of driving in electric mode. And it goes from 0, where we're driving all in gas mode, to 1, where we're driving all in electric mode. And these lines here are showing as you increase in the use of electricity, generally your emissions go down. And these line colors correspond to the different grids in the US. And you could see this grid here uses a lot of hydro, like you are in Quebec here. But there's 2 grids in the country that actually result in an increase in greenhouse gas emissions in driving in electric mode, and they're located here where there's heavy use of coal. So the sourcing of the electricity really influences the life cycle performance of these vehicles. We're doing work with China on this, and they have a big program to push for electrification of vehicles. Well, this is what that push is going to lead to. We're actually increasing. Until they change their grid, they're actually not helping with regard to climate change in terms of electrification. Want to take a step back and look at a bigger evaluation of mobility, and this is the iPad equation, which we talked about at our roundtable this morning, which relates the impact of an activity with the population, the consumption per capita, and the technology, which is the environmental damage per unit of consumption. This was developed by an ecologist and a physicist, Holdren, who's now the chief scientist for President Obama. And what I did with this equation is actually operationalize it. So I looked at automobile use in the United States and looked at impact in terms of gallons of fuel, which increased from 1970 to 2009 by 66%. What was driving that, the population went from 200 to 300 million, which increased 51%. Our consumption, vehicle miles traveled per capita, almost doubled. And then the T term, which is the inverse of the fuel economy, gallons per mile, on-road average went from 13 to 20. So that's an improvement, but the technology wasn't significant enough to offset our increases in population and our consumption pattern. Now we have policy to drive improvement on the T term. So by 2025, we're going to get up to 54.5 miles per gallon. Now that's new model vehicles. So this is going to improve, and I expect that this will probably start to go down. Our population isn't growing that rapidly, and we're kind of saturating on VMT. But one of the problems is if you put the iPad equation in a global context and look at China, India. In China, there's less than 100 vehicles per 1,000 population. In the United States, we have about 1,000 vehicles per 1,000 population. So we can't do it all with technology. I think this is one of the points I want to make here. Now, I want to compare Canada and VMT with the US. Actually, you're doing better. So this is miles per capita, 6,000. This is 2011, almost 10,000. But policy does matter. And actually, your prices for energy, for gasoline are actually higher than the US, which I think does have some impact on our consumption pattern. And this is the total price of gasoline, which includes the tax and the cost. And the cost generally, if you look across Europe, the US is the same, but our tax is much less. So if you increase the price, that will have an effect on our consumption pattern. If we look across modes, so if we're talking about sustainability, obviously we need to move away from resource-intensive automobiles to other modes. This is looking at the energy intensity, BTUs per passenger mile, and there's some surprises. You actually see that transit buses consume more energy than cars, which is maybe surprising. And rail, we think, could do better. So there's something that's driving this pattern because it doesn't really seem to make sense. There's some metrics there that I want you to look at and see if you could figure out what they are. Because that's giving you the answer why the intensity is following the pattern it is. Passenger load, very good. That is the vehicle occupancy. So we could load up many more people in our trains, many more people in our buses, only 9. Cars, 1.5. So occupancy is a representation of utilization of our technology. And this is indicating, in many cases, we're heavily underutilized. Now, coming over on the plane, I was packed in. We're utilizing our planes very well, so the efficiency is quite good. If you look at cars, SUVs, a larger vehicle, the occupancy is only 1.9. If you look at commuting to work, it's 1.2. And you can't go below 1, I don't think, unless you physically, sometimes the person's there, but mentally, maybe not. So these are important drivers in terms of mobility. So just to sum up that one, the use phase tends to dominate our impacts. Our efficient modes are really underutilized. If you look at trains and buses, we have the technological improvements on the horizon, but they are clearly insufficient to deal with our patterns of consumption, particularly if we look in the global context. We are going to need more market signals, and regulation isn't going to do it itself. We are going to need something like a carbon price to really put the true value of the cost on energy, and we are going to need to shift behavior. And that includes our patterns of development, which affect our need for transportation, And clearly, we're going to have to change our modes and really do better with our utilization of these vehicles. Want to switch now to residential homes. So this is a house in Ann Arbor that we modeled, 2,400 square feet. We took this house and we redesigned it, basically implementing off-the-shelf technology, focusing on insulation, efficiency, in terms of appliances, windows, heat exchange, some basic stuff. And we then looked at the life cycle performance over 50 years. There's about 300 tons of material go into a house. The energy went from 16,000 gigajoules, which is 16 cars. They were 1,000 gigajoules. Went down about 60-some% with existing efficiency. Now, what does that do to the life cycle? The dark bar here is the energy embodied in the construction and materials. The use is 91% for the standard house. As you go more efficient, the energy efficient house becomes more, the construction becomes much more significant. If you go to a zero energy house, then we're really shifting to the materials and the construction, which we were just talking about previously with steel and concrete. Those become more important. Let's look at the cost. So we worked with this model, this developer. He was not keen on our design. And the big factor was the price of the house went up from $240,000 to $262,000. It went up $20,000. Here are the life cycle costs. Here's the mortgage, here's your utilities, here's maintenance. As you go to the efficient house, you see that the utility costs are reduced dramatically, but the mortgage offset the gain, so the total life cycle cost was about the same. But my hypothesis for sustainability is if you follow what is environmentally sustainable over the long term, it is going to be the economically sustainable option. So what happens to prices of energy over time? They typically go up. So I recalculated this recently, and you could see, you start to see a shift. So now the efficient house actually comes out ahead because our utility prices have gone up. Let's look at, so one of the things we need to do is transform also the appliances within the house. And so we did some modeling on what is the optimal replacement for refrigerators, depending on different objective functions. And looking over the horizon of 85 to 2020, if you want to minimize the energy use, you would change out your refrigerator this frequently. And that includes the energy associated with construction of the refrigerator, the manufacturing. Here's greenhouse gas emissions, but from a cost point of view, it's hold on to your refrigerator. You can see here, because of the high initial cost, we're over 15 years in terms of the life. But we did do an analysis from the perspective of a current owner at the time, and if you have a refrigerator older than 94, you should replace it based on cost and energy. And I would say for refrigerators today, it's somewhere in the, if you have something in the range of 2000 or 2005, you could replace it, save money, and save energy. Patterns of consumption with houses in the United States. So we increased over this period 67% in terms of square footage. Is that because our household size increased? And did we have bigger families over that period? Well, let's look at the occupancy. So we actually decreased. We went from 3 down to 2.5 people in a house. Okay? Houses bigger, smaller family size. So this is not a sustainable pattern. If we look at size in the US, this is in square meters versus Australia, Denmark. You could see significant differences. UK, dramatically different. Interestingly, in Europe, though, the household size is a little bit lower than here, 2.4. The occupancy is a little bit lower. That's our standard up there in the corner. So if we look at drivers for buildings, again, the use phase dominates currently. Our patterns are not sustainable in terms of consumption. But where we need to focus is on the existing stock. We have new construction. but it's dwarfed by the 100-some million homes that we have in the United States that exist. The technology exists, but one of the barriers is the initial cost of that technology, even though it results in a lower life cycle cost. To overcome that, we need codes that actually deal with existing construction. We do not have those codes. We also need more incentives to help promote the adoption of new technology. Last system I want to talk about is food, and I haven't eaten yet. I'm starting to get hungry. I think this is going to make me more hungry when I start to think about the food system. But we're going to look at production and consumption of food, a life cycle approach, and we developed a model to look at sustainability indicators for the United States, some 50 indicators looking at environmental, economic, and social indicators. I'll share some of those with you. First, how much of the dollar do you think goes to the farmer? Well, in 1975, 40 cents out of the dollar went back to the farmer for growing the food. The other 60 cents is in marketing and distribution of the food. Latest data that was available in 2006, that went down to 19 cents. And if we continue this trend, basically we're going to reduce what goes to the farmer. I guess we're going to be eating virtual food. It's all going to go into marketing of the food. So that's an indicator that's not quite sustainable. If we look at the flow of resources associated with our food system, this is showing you the feed that goes into animal products. These are the crops for vegetables and grains. And this is what we consume over here. 26% of edible food is wasted. So if we could reduce our consumption on this side, we have dramatic benefits in terms of reducing footprint on the production side. If we look at the energy, in the United States we use about 100 quads of energy. 10% of it goes into the food life cycle. And we could break that down in terms of each of the phases here. Something got messed up with this slide, but this is actually looking at the production. You could see there's a lot of energy going into fertilizers. That was the processing. And then in terms of our consumption, refrigerators, back to the refrigerator theme, uses a lot of energy, some 42% of the energy in our consumption, storage, preparation of food. If we stack that all up, this is looking at the energy going into food, and this is what we consume. Actually, this is what is available, the food output. It's about 7 to 1, or you could just remember 10 to 1. For every unit we consume, it takes 7 to 10 times that in terms of the life cycle. For the United States, that food availability is 3,900 calories per person per day. I don't think we need 3,900 calories. So there's a huge opportunity dealing with our consumption and dealing with waste. And a consequence of our consumption is an epidemic problem, which is obesity. And actually, again, you guys are doing a little bit better than we are in the United States. Obesity rate in the United States is over 30%. It's 32%. In Canada, it's 24.3%. Okay, this is a global problem, and it results in diet-related disease. It drives the whole production and burdens associated with food. So let's talk about obesity. I'm actually going to have you calculate what's called the body mass index, which allows you to classify yourself as underweight, overweight, or obese. So I want you to take your weight in kilograms and divide it by your height in meters squared. I'm going to give you about 10 seconds to do that. You're all a lot of engineers out there. Actually, I'm going to help you. So here's a table. What you do is you take your height over here. So find your height. I'm 6 foot. And you work across until you find your weight. And I'm actually right on the line here. And you go up and you read your body mass index. Does everybody find their, hopefully you're on the chart somewhere. Does everybody have their number? All right, so I'm going to go back so you can classify yourself. I'm actually on the edge. I'm overweight, and I'm close to, I could be obese after dinner tonight. So this is now, this is an indicator of health, but, you have to look at a lot of other factors in terms of, your construction. It doesn't mean you're unhealthy if you're overweight or obese, but consumption is a big problem with the food system. And one of the things that's leading to it is just how we really emphasize portions. There's something called portion distortion. So back 20 years ago, a plate of pasta was 500 calories. What do you think a plate of pasta is today? I'll give you the answer. 1,000 calories. So twice, you go to a restaurant, and it's great stuff. So you're gonna consume that. All right. Well, that's driving the whole life cycle of the food system. So we have to reduce our consumption, but we also have to look at what we're eating. So this is looking at greenhouse gas emissions of the diet and losses in the United States. And you can see the one that stands out, you probably know this, is meat. This is what we consume. This is what we waste. Then you see up next is dairy products, poultry, all the good stuff, the fats, the sugars are here. Here's the vegetables. So we're doing working with nutritionists on looking at what is optimal from an environmental point of view, a nutritional point of view, and an affordability point of view. So we sum up the food system opportunities. If we look globally, there's problems with food security, people not getting enough food. And then on the other side, there's overconsumption leading to overweight and obesity. The greatest leverage point in this system is our consumption and opportunities to reduce our waste. We also need to look at diet shifts, and there's opportunities clearly to reduce our greenhouse gas emissions from that. And we've been working on this with the National Institutes of Health. We're focusing on policy. Unfortunately, our ag policy is about promoting production of agricultural products. It's not looking at what we're delivering, and we need to connect our production with the goal of food, which is, our enjoyment of it, but also the nutritional value, and our policies are not oriented that way. I'm not going to sum this all up. I'm just going to go to a thank you slide. I really appreciate the opportunity to talk to you about these systems and where are their lever points to help with transformations. So thank you for your attention.